Yeah.
Okay, good. All right, next speaker is Fai Mak from Cornell. You heard part of introduction yesterday. Your continuation today.
Okay. Yeah.
Thank you.
Okay. Do you hear me well? Okay. Cool. Let me check this. It's working. Okay, it works. Cool. So, you heard about how to make some of the moray structures, and G told you a little bit yesterday about the basic optical characterization. So today I will tell you a little bit like why this material is fun for doing some physics. So it's a more physics-oriented talk. I'll tell you a few examples of what you can do with this class of material called semiconductor moray materials. Okay, so that's the goal. So very brief reminder of the basic ingredient. The building block of this material is this monolayers of transition metal dichocalcinide semiconductor. Each layer of this has 3 layers of atoms, with the middle layer being transition metal atom. That you now should be very familiar with this structure here, and then encapsulated between the chalcogen atoms. And if you look from the top-down view, it actually has almost the same structure as graphene. That is a honeycomb lattice structure, except that now the 2 sublattice sides here and here are occupied by different atoms. One side is occupied by the transition metal atom, the other side is occupied by 2 chalcogen atoms on top of each other. So it forms a honeycomb lattice structure. And when you go from the real space to the momentum space, it goes to also a hexagonal brilliant zone with the zone center at the gamma point and the zone corners at the K and the K prime points. And these 2 points are different. They are actually time reversal partners from each other. And the very basic electronic structure of this material is actually quite different from the conventional semiconductor. The band gaps are located at the gamma point. This material in monolayer limit, actually the 2 band gaps are located at the K and the K prime corner of the brilliant zone. So basically a very simplified band structure without spin-orbit interaction is something like this, that you just have 2 copies of direct energy gaps at the K and the K prime. And they are actually time reversal copies from each other. And for the intrinsic material, you have no doping, that the Fermi energy, which is this dashed line here, is located in the middle of the band gap. Of course, you can move this Fermi energy by the gating or by just a substitutional doping that will move it closer to the conduction band or closer to the valence band for a N-type or P-type doping. Okay. So this is the building block for a more complicated material, which is this semiconductor moray system. And there are 2 ways that you can actually make this material. The first way is that you just use the same layer, and I'll tell you a little bit about how to make them. And you put another layer on top of each other with a small twist angle, because the 2 layers are exactly the same. So you have to give it a twist angle theta here in order to generate this interference pattern between the atoms. And so that once you do the twist, you can see that there is a periodic moray structure or a structure coming out from this twist angle. And the typical moray period that we talk about, or this superlattice period, is about 10 nanometer, which is almost 2 orders of magnitude larger than the atomic scale. And the moray period here, A sub m, is given by A, which is the original lattice constant, the atomic lattice constant on the angstrom level of the material, divided by the twist angle theta measured in radian. A different way to create a moray heterostructure is that you start with 2 different layers of material. For instance, here the example would be tungsten selenide on top of tungsten sulfide. And you don't need a twist angle in this case. You generate a moray pattern even as small as 0 twist angle, because there is a finite lattice mismatch between the 2 materials. For this particular case, it has a 4% lattice mismatch. So that you just put the 2 on top of each other exactly at 0 angle. You just generate a pattern like this, and with the moray period also on the order of 10 nanometer. And in this case, the moray period, A sub m, is roughly given by A, the lattice constant, again, divided by delta here. Delta is the lattice mismatch. In this case, just 4%, then your A divided by 0.04 is about, also about 50 times or something like that of the atomic length scale. Okay. So how to make them? So there are some differences in terms of making the homobilayers or the heterobilayers. Homobilayers, people usually just do this tier and restack method. So basically, what you do is that you start with a single layer of this material from mechanical exfoliation, this step 1 here. Then you use a polymer film to stick to half of the or part of the film here. Then you just lift it up, so you tear the original layer into half of it or just part of it. Then you rotate the stage here by some angle theta, and then you just restack the material on top of each other. Then you just encapsulate the structure between boron nitride substrates and be happy and measure it. Okay, so that's one way to make the homobilayers. The heterobilayers is a little bit different because you don't start from the same layers on the substrate. So you actually do not really know the relative angle between the 2 layers, right? The 2 layers are actually on different substrates to begin with. So there would be some difference in this step here. You just cannot, tear them apart and then reassemble by just rotating an angle. You have to know the crystallographic orientation of the film first. So what we typically do is to look at the second harmonic generation. And what you do is that you have a film here. You blast the sample. Well, you really just shoot. You don't really blast, you just shoot the laser at 800 nanometer. And then look at the emission at 400 nanometer. And that emission is actually very sensitive to the crystallographic orientation of the sample. For instance, if you rotate the sample, you will see this periodic pattern, about 6-fold symmetry of this pattern coming out, of the light coming out from the sample. So you will just do this for each of the film. For instance, the blue dots are for the tungsten sulfide film, and the red dot is for the tungsten selenide film. And before you align them, of course, this periodic pattern, they don't really align on top of each other, right? So you do the crystallographic orientation, then you align them. Now they're nicely lined up on each other. And then you know the crystallographic orientation, you put them on together. And now you can generate the Moiré heterostructure in this way for the heterobilayer. So the difference is only like in this step, you cannot just rotate an angle. You have to do this extra step here. Sorry, to characterize the crystal orientation. And this additional thing, quite nice coming out from this second harmonic generation technique is actually that there are 2 ways to actually, there are 2 different ways to stack this heterobilayer on top of each other. Because each of the monolayers is only 3-fold rotation symmetric, there's a difference. You stack them on 0 degree or actually 180 degree, they are different. So you can actually just look at that, the resultant second harmonic generation, which is the gray dots here for the finished heterostructure. And it is actually weaker compared to the constituent layer. And that means actually in this case that we have the 2 films at 180 degree aligned to each other. That would give us the destructive interference of the second harmonic generation, and you get a much weaker second harmonic generation. Yeah.
Just a question about the second harmonic measurement. Is this a commercial system you have, or is it something more specialized that you develop?
We build in our lab, but I believe that you can. I'm not so sure whether there are some commercial systems. It's easy to do, actually. It's easy to set up, yeah.
And cost?
Cost would be mostly on the pulse laser, yeah, which is about 100K for the pulse laser. Cost is mostly that. Yeah. And if you happen to stack the 2 layers, I don't have an example here, at exactly 0 degree, then this one is actually stronger than the constituent because of the constructive interference. And you can see that quite nicely. So you will exactly know like what kind of stacking you have for the structure. Okay. And after you finish it, you can also ask your friend to do the TEM. And our friend said Müller at Cornell. And you can actually see this is a nice TEM picture of this particular aligned Moiré structure, molybdenite on top of tungsten selenide. And you can see the small dots here are the real atoms of the material, but on top of that, you can also see the extra periodic pattern of the long wavelength modulation due to the Moiré interference pattern coming out from the interference of the atomic structure. And it has a pretty good triangular lattice structure for the Moiré system. Okay. So with this introduction of how to make this structure, now let me just go to tell you a little bit about the basic feature of the electronic band, or the basic feature of why this system is so interesting and so unique compared to the usual atomic scale quantum materials. We just call them atomic scale quantum materials. Okay, so the first thing you may ask is actually that do you still have the Bloch's theorem for the electronic bands? And because actually this is a good question to ask, because you look at this structure, it looks like periodic, but at each of this site here, the atoms are not exactly on top of each other. So that means that in the real atomic scale, there's a small difference from this side to that side to that side. They look slightly different because of the exact alignment of the atoms. So there is no guarantee that this Moiré heterostructure is really periodic. Then you may just ask, if I don't have an exact periodic structure, whether the Bloch's theorem still applies. And the lucky thing that we have is actually that when the angle, twist angle or the lattice mismatch is very small, which is the case that we are usually dealing with, and there is a large separation on the length scale, meaning that the Moiré period now is much larger compared to the atomic distance. And I'm saying that this is 10 nanometer, this is on the order 1 angstrom. So it's almost 2 orders of magnitude difference. But there's a very nice separation of the high energy physics and the low energy physics. The high energy physics is governed by the atomic scale. The low energy physics is really governed by this smooth atomic scale. So to a very good approximation, because of this large separation of length scale, that you can almost forget about the original lattice. So you can forget about these tiny dots in this pattern here. Forget about the high energy physics and just look at the low energy. And what you can do is basically treat that there is an electron with a certain mass given by the band mass of the original lattice, and then moving in a smooth periodic structure defined by the Moiré pattern. And this, in this sense, it's approximately periodic. Then the Bloch's theorem still holds. And what you can see is just that this is the original band structure of the monolayer material. Once you introduce a smooth periodic structure, it goes through extra Bragg reflection, and you reduce from a big Brillouin zone to a small Brillouin zone, and you just produce a series of these Moiré mini bands. So you just need to think of it like a zone folding picture for the creation of the Moiré bands. Okay. And the next thing, you actually can also think of each of these Moiré sites. We call each of this is a Moiré site here. Is on the order, the separation between the site is about 10 nanometer. You can think each site as like an artificial atom or artificial quantum dot or something like that. And each atom provides a trapping potential for the electron. The electron can trap inside in this potential. And the trapping potential depth is on the order of 100 to 200 milli electron volts. Okay. And so you can think of this is like an emergent atomic scale in the system, this 10 nanometer. It defines a much smaller atomic density rather than 1 over angstrom square. Now you're actually 1 over 10 nanometer scale squared atomic density. So this is about 0.1% of the real atomic density. And this is significant. What it means is actually that now it's very easy. I'm going to tell you the device structure that we use, but it's very easy now to just use skating to sweep your Fermi energy through multiple of these atomic levels or the bands in the heterostructure. Okay. And this is actually pretty important here because every time you sweep the Fermi energy through the entire band, it's almost like you think about a periodic table is really like you move 2 elements to the right in the row. So it's actually really important that you actually, every time you change the Fermi energy through half of the band, it's like you change to a new element in the periodic table in this sense, when you think in terms of this artificial atom. Because of, again, because of this emergence of the new length scale in the system. And you can carry this analogy further, actually, to really think of it. This is a sort of the idea from Ellen McDonald, that you can think of it as building an artificial periodic table. You start with the artificial atom, then you load the electron into this artificial atom. The first electron you load will be like artificial hydrogen. The second electron will be artificial helium, and then lithium, and so on and so forth. Of course, this is a 2-dimensional periodic table, so the atomic orbitals will be a little bit different. So in a recent experiment, long story short, you can we actually create a material that can load electron into this system, And each of this peak here, integer filling, is basically representing each electron you load into this artificial atom. And you can load up to about 8 electrons. So you can sort of like, really 8 different elements, artificial elements in this system.
What about the symmetry of these occupied bands?
Yeah, so that actually, if the band structure is really this simple, like here, that you can actually design material of almost this simple lattice structure, is that you make the 2 layers of very large band offset. Then you just have all the orbitals from one of this layer. Then that picture is quite correct, I would say. The bands are not so complicated, but if you have to bring the bands closer to each other, then you have hybridization between the 2 layers. Then you sort of reset at some point, right? So that picture of, building this periodic table is more complicated than that. Yeah.
Can you totally ignore disorder of the atomic lattice?
In theoretical sense or practical sense, let's say the practical sense we cannot, because that also defines the mobility edge of the measurement. But theoretically, as long as you have only a few of them, I think that wouldn't matter in terms of the low energy physics, because as long as it's not like a long scale Moiré disorder, that wouldn't change this flat band too much. The flat
So
band.
normally you don't work in your measurements.
Yeah.
I just wanted to ask you to clarify what you were saying to give these questions. Are you saying that basically if you make a large band offset between them, or if you choose a band offset between the 2 materials, that you just think of one of them as providing a potential, on the other that's your conductions?
Yeah.
I see.
Yeah. Then the orbitals is quite simple. Right? Then the orbital structure is quite simple in that case. But you can also do the other way to bring the bands closer, and there are also interesting things happen. For instance, you can create topological bands, and I hope I have some time to talk about that. Okay, so third unique character of this emergent link scale of about 10 nanometer is that the electrons are strongly correlated, and simply because you make them further apart. Okay, so by this trapping Moiré potential here, the electron find it much harder to hop from side to side. You can think of it, if this Moiré trapping potential is very deep, then the electrons are very well localized by this Moiré trapping site here, and it's becoming quite difficult for the electrons to move from side to side. So typically, this tunneling energy scale of the electron from side to side is on the order of 1 to 10 milli-electron volt. You can also estimate, if you put 2 electrons on the same site, just using the Coulomb expression for the Coulomb repulsion energy, E squared over the dielectric constant, and A here, sorry, A is not the atomic length scale. A here I changed to the 1-year function size of the localized electron wave function, and you can estimate that this is on the order of 100 milli-electron volt. So the repulsion energy is actually often many times of the tunneling energy scale here. So it's in that sense that the system is strongly correlated, that the interaction energy is way stronger than the kinetic energy of the electron. I'll talk about that more. And finally, the final characteristic is that the bands are relatively simple. I'm just pulling out this particular energy band structure of this particular heavy fermion compound. We call it the atomic condo lattice here. And you can see that there are many different noodles of spaghettis in this band diagram here. It's quite complicated, and this is where the Fermi energy is located around that level. And it's a very interesting compound. It shows, heavy fermion physics and quantum criticality and so on. But it's sort of, you can look at this, it's sort of hard to understand some of the essence of the physics in this material. But if you actually have a Moiré heterostructure, you can just always engineer the bands that you can tune your Fermi energy near the top of one band, and they have relatively simple band structure. For instance, you can create a Moiré condo lattice in this case, that you have the upper and lower Hubbard bands, and then you can put in a more dispersive Moiré bands in between. So the band structure, the exact detail is unimportant, but I just want to point out that the band structure can be typically quite much simpler compared to some of these atomic scale strongly correlated materials. Okay, so the simplicity is also a nice thing of these materials. So this is the outline of the talk. I'm going to give you two examples of what one can do with this system. Two examples on physics. One is the Hubbard model physics. The other is the K-Malay model, of the realization K-Malay model in this class of material. But before that, I would like to just pause and ask if there's any question on some of the basic stuff. And probably that's the most important thing I want to tell you about the basic stuff regarding to the structure and the electronic structure of this material. Yeah.
You mentioned that it's very like the easy bands. Was it calculated or like how you say? If you go back, like with the it's probably calculations on the left side.
Yeah, this is actually the calculated band structure.
Is it calculations as well? Or?
Oh yeah, actually, you can engineer a certain type of material to create a Moiré condor lattice, and the mean field band structure looks something like this. Yes. Yes. Yeah.
So, what kind of excitons do you have in such systems?
Excitons. Yeah, that's also an interesting question. It depends on whether the exciton binding energy is smaller or larger compared to the Moiré trapping depth. If the exciton binding energy is very large compared to the Moiré trapping depth, then the Moiré trapping depth is like a perturbation on the exciton. Then when you measure the optical transitions, they don't look particularly different from the constituent monolayer. But if your trapping depth is very deep, which is indeed true for some of the material, then the exciton binding is sort of on the opposite limit. There is a perturbation compared to the trapping. Then you can totally modify the optical absorption spectrum, which G yesterday talked about, that you make one peak into multiple peaks because of the extra periodicity. Yeah. Yeah.
So in the picture you showed earlier, you had the rotational Moiré pattern and then the heterostructure Moiré pattern. For me, the heterostructure one looked like you have two super atoms per unit. So is that the right way to think about it?
You are talking about this thing here?
Correct. You have the green and the orange.
Yes, it's more like the different sides of the Moiré. So you can actually, this is really the unit cell. Well, this is actually not, this is not the unit cell. These three sides are the triangular lattice structure. But you can, you also have two different sides. You have this side and that side, and also this side. So you have three different sides. It depends on whether it's here, here, or there. So it's just the different sites within the unit cell. And they may have like for instance, this site may be a potential minimum, and that site may be a potential maximum. So when you put the electron will just go to here instead of going there. So when you look at this, they're just like different sides of the unit cell. Right. But they typically correspond to different potential. It's one is usually a minimum, the other is like a maximum. Right.
So I guess because the analogy would be you had two atoms and you have double the bands or whatever.
You can also, you can also have sometimes even these three different sites, you can have a local minimum, additional local minimum for that. Then you can also think of it that I have two atomic sites, and it becomes something that's called a charge transfer insulator. And then when you put the first electron, it will go to this side, the second electron, it will go to that side because of Coulomb repulsion. So it's a bit like, that's a charge transfer type of picture. So it has some analogy also with a local picture of chemistry as well.
Thank you.
Okay, yeah.
What do you mean by the artificial not swapping out?
Yeah, let me elaborate a little bit more on this. Is that this is actually like an artificial atom. What is an atom? It's just that you have a trapping potential. But this atom, of course, is actually quite different from the real atom. The real atom is 1/r potential, that it goes all the way to infinity at zero distance, right? But when you solve the Schrodinger's equation for a single, like a proton with an electron surrounding it, you have the s orbital, the p orbital, and the d orbital, and so on and so forth. You have something similar to here, except that this is more like a harmonic trapping potential, but you can still have like the s, p, d type of orbitals in the system. And it's in that sense that you can sort of build an artificial Moray periodic table in that sense, because the first electron has to go to a spin up state, let's say, of the s orbital. The next should go to a spin down state of the s orbital. Then the next will go to a p state. But it's two dimension. So your m is only like 0, +1, ±1, or ±2. So you have to make it your periodic table that is different from this 3-dimensional periodic table. You have to take into account that, now that the d orbital do not have really 5 different orbitals, but actually it still only has 2. This is only ±2 and ±1 for the p orbital.
But you're still tuning it by swapping out elements.
The orbit's already there, and you just load the electron depending on how many you add. That will have different.
I mean, does the lattice change if you have like, I don't know, selenium instead of tellurium?
Yeah, actually, you can almost forget about the original. Yeah, you can almost forget about the original atoms. It's really all defined by this smooth periodic structure. You can actually change the landscape of the periodic potential by changing the phase of the tunneling and so on and so forth. I'll mention a little bit about the Moray potential. The Moray potential is actually related to the periodic modulation of the interlayer tunneling. And that periodic modulation can have a phase. And if you have a phase there, you can change the Moray potential landscape. And that can change, so-called, can sort of think of it as a change of the atomic structure of the crystal. But you can forget about the original, material. Selenium, tellurium, it's no longer important. Yeah.
So in case of real atoms, we consider like a spherical symmetry of the orbitals. What would be the ideal symmetry for the Moray atoms?
Yeah, so interesting question. Of course, if you really have like an isolated atom, it's going to be spherical symmetric in the 2-dimension, but it is not perfectly spherical symmetric. It's in a hexagonal arrangement. So it's also 3-4 rotation symmetric. You can think of it that you still have a crystal field effect on this. So when you calculate the band, the symmetry of these levels still has to be split according to the crystal field of this Moray superlattice structure. But it's not so complicated because the d orbital is only ±2. There are only 2 of them.
I think I'm a little confused. So we make analogy with atomic orbital, then in the atomic orbital, we only think one atom, but here we actually have a lattice. It's more like a band, right?
For only an isolated case that you have an atom, then of course the tunneling between this atom will produce a band. And then how the different atomic levels will split then depends on the crystal field, right? On the symmetry of the lattice. But usually we are dealing with honeycomb or a triangular lattice. Yeah. So yeah, you're correct. They are not isolated atoms, and the tunneling would just mirror the atomic orbitals into bands. So you can just sort of think of it. This is the first S band made of the S orbital, right? The second will be the P. Then there are 2 of them for the P orbital.
What about the inter-atom distance? How close can you get them for this picture? Before the underlying lattice starts.
Oh, it's a
the band, the bands.
Yeah, it's a little hard to answer, like whether there's a sharp bound. I think it's a crossover, very smooth crossover, and nobody really knows like at which point that you should think of the underlying atomic structure. At some point you have to take into account, of course, if it's really rotating at 20 degrees, then obviously that the atomic structure is important. But at which point I think it's a smooth crossover.
On your beautiful TN images, have you done like views, and can you see like band changing, like band structure?
We have not done more sophisticated than that. Yeah.
But it's localized, as you say, and like
Yes, you definitely can do use, and you can learn about the energy levels of each of the sites. Yeah. And I think some people have done that to look at the Moray exciton, where the wave function is. Yeah. Yeah.
What factors will decide the Moray potential depth?
Yeah, interesting question. Then it's related to the question of what gives rise to the Moray potential. There are two contributions. One I already mentioned, that you put the two layers on top of each other, the electron have a tendency to tunnel from one layer to the other, and the tunneling would get the tunneling amplitude would get modulated in this length scale here, because the tunneling at this side is slightly different from this side and that side, right? So the tunneling is smoothly modulated, and that is one contribution to the Moray potential, which is a modulated interlayer tunneling. The other is actually that these materials are relatively soft. When you put them together, and they can have a they can have a three-dimensional reconstruction, like Dave Manders yesterday mentioned. And because the energy gap of the system is strain dependent, when you have a periodic modulation of the lattice structure, you can think of it as a periodic strain field. And then the band gap is also dependent on the strain. So that acts like an additional periodic potential to the system. So usually there are these two major contributions to the Moray potential. One is related to the atomic reconstruction, the lattice reconstruction. The other is the interlayer tunneling. Interlayer tunneling.
Okay.
Yeah, fine. Okay.
There's only one I want to ask. So is there a way to track, like suppress tunneling? Electrostatic. Tunneling, is there a way to
suppress the tunneling? Yeah, actually the tunneling you can control very well, and I'll give an example that the tunneling is a resonant process. So if you have bands from one layer, bands from the other layer, if the two bands are close in energy, then the tunneling is resonantly enhanced. But if they're far apart, they are not resonantly enhanced. So in that sense, by just changing the distance between the bands in the two layers, you can simply do by applying a vertical electric field, then you can actually change the Moray potential trapping depth. You cannot change the contribution due to the lattice reconstruction, but you can change the tunneling type quite well with the electric field. So that's a very nice way also to tune sort of the trapping potential depth or the band structure of the material. Okay. So I will just maybe given a limited time, I probably will only be able to talk about the Hubble physics, which is totally fine. And I'll just give you 10 minutes. Yeah, about 10 minutes. I'll see. Yeah. So very brief on what is the Hubble model. The Hubble model is quite simple. It's invented by John Hubbard and Kanamari and Caswiller in 1963. But then somehow the last two people are forgotten, and it's just known as the Hubble model. And there are only two terms in the Hamiltonian. It's really just a very simple, really like the physicist approach to take into account of interaction in a very simple way. Okay, so there are two terms. The first term is actually the tunneling of the electron between the lattice sites. And if you only have these two terms, if you only have this term here, is solid state physics 101, that is a tie binding model, then you broaden the atomic levels into bands. And the additional term that actually added by these three people here is that there is an on-site Coulomb repulsion. If you happen to find two electrons on the same site, it has an energy penalty, which is U here, that the electron, because they repel each other, they don't really like to be on the same side because they cost more energy. But of course, you can say like, oh, the electrons really interact with long-range Coulomb interaction. But this is really a very simplified approach to deal with, the many particle interaction in the system. So only two terms, tunneling term and the on-site repulsion term. And it's written in the second quantization form would be something like this for the Hamiltonian. And these two terms actually would tell the electrons to do totally opposite thing. The tunneling would actually tell the electrons to delocalize as much as possible. And that would just gain kinetic energy. They tell the electrons to move around as much as you can. But the U would actually tell the electrons not to move around too much, because if you move around too much, you may just end up finding another electron on the same site, and that causes you Coulomb repulsion energy. So it's really like, one is telling the electron to delocalize, the other is telling the electrons to localize. And this sort of conflicting instruction on the electron is giving rise to all this interesting physics that one can find in the Hubble model. Okay. And you have two terms, and so the one term you can sort of drop it, and the physics is really governed by the ratio here, U over T in the system. Okay, and why the Hubble model is important, I think many people still believe that is the model to account for many of the phenomenology in a high temperature superconductivity. And definitely it's playing an important role in accounting for the physics of magnetic insulators, some type of metal insulator transitions, and so on and so forth. So it really can explain many of the complicated observations that one can make on many of the solids. Okay. But there's a problem of this very simple model. It only has two terms. The problem is actually that it almost cannot be solved, except for the 1D case. And for 2-dimension and 3-dimension, which most of the materials are in that category, you cannot solve the Hubbard model in 2D and 3D. Okay. You can try to do certain numerical approximations and try to solve the model numerically, but you need actually a reference point. And so it will be very important to have some experimental realization of the Hubbard model to serve as a benchmark for many of these numerical studies of the Hubbard model. And there are actually such simulations of the simulators of the Hubbard model. And one famous example is these co-atom simulators that you just shoot lasers in all 3 different directions and generate an interference pattern that look like the Moray trapping potential, but in this time is really created by the laser beams rather than by the interference of the atoms. Is interference. The light here, then you create this a periodic structure from the interference of the light. Then you load atoms into each of these sites, and you can simulate the Hubbard model, and people have done that. But usually they're doing it in a totally different regime from what I'm going to tell you. And you can also do that because I told you that you can think of the Moray trapping size like an artificial atom. And if this is the band structure of one of this particular combination of tungsten selenide and tungsten sulfide, this is the bands from the tungsten selenide layer. This is the bands from the tungsten sulfide layer. And we chose this particular compound for illustration because these 2 bands are very far apart, especially the valence band are very far apart from each other. So the atomic orbitals are quite simple here. And if you just look at this isolated band of the first Moray band on the whole side of the tungsten selenide layer, and Alan McDonald and colleagues have shown that the low energy physics can actually be just mapped to a Hubbard model. That there are only 2 terms in the Hamiltonian, again, that the electron will hop in this triangular lattice, and also there is an on-site Coulomb repulsion term for the electron. Okay. So this is another kind of a simulator, and analogous to the atomic scale, to the co-atom simulator that one can do in a solid state setting. So this is a device structure that we make this material using the approach that I told you. We encapsulate between boron nitride, which are very good insulators. And then you further encapsulate between top and bottom gates. They are just metallic gates that you can actually apply voltages into these 2 gates. And you can tune 2 things because now you have 2 gates, you have 2 degrees of freedom. One is that you can do a symmetric gating. For instance, you can apply 1 volt here and 1 volt here. And that will just shift the Fermi energy of the entire structure without changing the bands of the material. And that's just changing the Fermi energy or the doping density in the material. Or you can apply anti-symmetric gating, meaning that, for instance, you apply 1 volt in the top gate and minus 1 volt in the bottom gate. Then you don't change the electronic density in the system, but rather you just apply a pure electric field through the material. And that can just realign the bands because the bands are from the 2 different layers. And if you apply a vertical electric field, you put a potential difference between the bands, and the bands will just move with this electric field. Yes. All right. And the second tuning, actually the electric field, as I mentioned, you can actually tune the potential trapping depth for the Moray atom. And this is a typical device structure. I think G yesterday already showed that you put additional electrodes into your material in order to just measure both the optics. If you just shoot laser in the center, you measure the optical property. And if you just flow current in these electrodes, you just measure the transport properties of this material, okay? So very simple example, the very simplest thing that one can measure is just to flow a current and measure the resistance in the sample. And this is a 2-point resistance. This is a kind of 1st generation device that we can only do 2-point resistance as a function of the doping density in the system. Okay, and this 1 here would mean 1 electron per Moray unit cell, one electron per atom, and this 2 here we just put to 2 electron per atom in the Moray heterostructure. Okay, And I just want to point out two prominent features. There are two resistance peaks. One very prominent resistance peak at 1 electron per atom, and then another resistance peak at 2 electrons per atom. Okay. So these are the only two features, and these are the two prominent insulating states in the system. So what are they? Okay. So first of all, the 2 electrons per atom, which is schematically shown here, that because of Pauli exclusion principle, you put 2 electrons per atom, they have to, as the spin will be anti-aligned. And in the band picture would be just that you have a total empty band and a total filled band, and the Fermi energy is located in between. And so that's a very simple band insulator because there's an energy gap at the Fermi energy. So it takes some finite energy to excite electron across the gap. So at low temperature, you cannot really do that. It becomes an insulator. Okay. Well, for 1 electron per Mori unit per atom, which is this case here, in the single particle picture, it corresponds to a half filled band. And you look at this, the Fermi energy has no gap. So it takes 0 energy to excite the electron, and it's a metal. So you just apply a voltage, the current should spontaneously immediately. So that would be the picture without any interaction. But with a strong interaction, I told you that the U term would tend to localize the electron at its site. That would be the configuration to minimize the total Coulomb repulsion energy. So it turns into a Mott insulator that the electrons fail to move around. Okay. So that would be in the limit of U compared to T much bigger than that, then there is a Coulomb gap opened at the Fermi energy, and now it's an insulator again. Okay. Well, this insulator is very different from this insulator. Okay. Of course, both the charges are localized in both of this insulator, but this insulator also has no life in the spin because the two spins are exactly, they form a spin singlet here, and that's really quite boring. Even for both the charge and the spin is quite boring. But this insulator here, each side has 1 spin. There's 1 moment here. So it's actually not a boring insulator because the charges, the charges are indeed localized, but the spin, they are active and the spins can talk to each other. And this is something that I already mentioned by G yesterday, that the electrons are localized, but you have the emergent local moments that the spin can talk to each other through the exchange interaction, like a magnetic insulator. And one way to show that there is really this emergent lattice of spin of local moment is to measure the temperature-dependent magnetic susceptibility. And the inverse of this susceptibility is going to be proportional to the temperature and follows the Curie-Weiss law. And you can measure the Curie-Weiss constant, which provides a measure of the exchange interaction between the local moments here. And G told you yesterday how we can do that. And this is just the data. Magnetic susceptibility versus temperature, or the inverse magnetic susceptibility versus temperature, same data set, just plot in different ways. And the black dots are the data points, and the red curve is the fitting using the Curie-Weiss law. And we can obtain the Curie-Weiss constant or Curie-Weiss temperature of -1 Kelvin. So the negative sign means that the spins interact with each other with antiferromagnetic interaction, which is totally expected for a Mott insulator because in the strong interaction limit, the spin can only go through a virtual tunneling process known as a super exchange, and that would give rise to a antiferromagnetic interaction. Okay. So I would say that this is really the data that shows that this insulator is different from the band insulator. The band insulator, then you will not get anything like this. All right. I think, I can give you. How much more time do I have? Or just, okay, yeah, I can just give. You know what? I'll just skip this. Oh yeah, this is actually about tuning the Maury potential depth. So we just apply a vertical electric field to tune the relative distance between the bands of the 2 layers, and indeed you can change the Maury potential depth. And when you do that, mostly you are actually changing the tunneling rate because the tunneling rate depends exponentially on the Maury trapping potential depth. But the Coulomb potential scales much more slowly with the potential depth. So by just tuning this potential depth, you're sort of tuning the ratio of U over T in your Hubbard model. And you can do something quite fun, induce a metal insulator transition in this area. But I will skip this. And so I just want to mention that this is quite an interesting Hubbard system that a lot of things actually have seen by people in the past few years. For instance, I told you about the Mach insulator filling factor 1 and the band insulator filling factor 2. G yesterday told you a series of electron crystals spontaneously arranged into patterns at fractional filling factors. And there are also some evidence of nematic states which are electronic compressible, but that they spontaneously break the rotation symmetry of the system. And you can also tune the bandwidth by applying an electric field to induce metal insulator transition. For instance, you can kill the Mach insulator by increasing the bandwidth by increasing the kinetic energy of the electron. One last example that I want to tell you is that in addition to sort of study Hubble model physics for electron, you may just wonder, well, electron is a fermion. Can we also do Hubble model physics for a boson? Which they follow totally different statistics, right? And it would be nicer to actually, you can do both for the fermions and the bosons. And there is actually one way to do it. And the system is a little bit more complicated. You can see that we have a moire layer here of the orange layer, and they are also encapsulated between the insulators and the gates. But on top of that, we also would add a single layer of material without any moire structure in this material. And the two are spatially separated by a very thin boron nitride layer of 1 to 2 nanometer. So they are very close to each other, but they do not directly talk to each other, at least not in the sense that they cannot directly tunnel between each other. The electrons cannot tunnel between the two layers. So if I draw the potential landscape of the two layers, the blue layer would be just that I don't have any moire potential in this layer. So it's a moire-free layer. And then the orange layer is the moire layer that we have the periodic modulation of the potential. You have the moire atoms in one of this layer here. And these two gates, you know what? They can actually tune the system to load electron in one layer and hole in the other layer. And the electron and hole, they like to bind to each other very strongly because of the Coulomb attraction, and they form an exciton. An exciton is a composite boson because the electron spin 1/2, the hole is also spin 1/2. When you put them together, they actually form a boson. And the periodic potential of the bottom layer would actually provide a trapping potential for the electron, but the electron is bound to the hole. So effectively, you provide a trapping potential for the excitons in the system. So in this case, you actually can create an exciton or a boson on a lattice, and the bosons can tunnel within the sites. And when you put two bosons on the same side, they also would interact with each other. So you can actually really create a system of doing sort of Hubble physics, not just for fermions, but also for bosons in this kind of a more complicated setting for the atomic structure. So I just want to give you an example of that. By just playing with the structure and playing with the band alignment, you can create, all sorts of interesting things of exploring physics in this kind of material. Okay, so I think I will just stop here. I don't have time to talk about the K-Malay, which is some kind of even more complicated topology stuff, but I will just stop here and happy to answer additional questions if you have. Yeah.
Thank you.
So in the orange part, there is already a two-layer system. So can this moire system already form into the external self instead of the orange and the blue part?
Yeah, you're correct that actually you can also generate excitons in just this layer here, right? But in order to generate those excitons, you have to excite it with light. So that would be a system out of equilibrium. And that's also very interesting. You can think about if I pump harder and harder and generate a higher and higher density of excitons by pumping harder under the system. And will the exciton do something? I shouldn't say it's ground state because it's actually totally out of equilibrium for the system. But you can it's still valid question to ask. The exciton are interacting with each other. What kind of state that could emerge? By just doing this layer, we can actually create fully equilibrium exciton. So these excitons, they just live forever. They are generated by electrostatics. They are generated by gating here. It's an equilibrium ground state for this exciton. It's not generated by light. is generated by just changing your gate voltage of the top gate and bottom gate, or you can also apply a bias voltage in between the two layers. So this is the nice thing is just a fully equilibrium system that you can just go to millikelvin temperature to measure it or things like that. So you just really study the ground state property. Yeah.
And also maybe a technical question, like how high you need to apply the voltage in order to generate the electron hole as a
So for instance, it depends on the band alignment of the system. And it has a type 2 band alignment for this case. If you really need to generate an electron in one layer and hole in the other layer, the band gap is about 1 volt, right? So you need to apply interlayer bias of 1 volt on the order. But you can reduce that gap a little bit by just applying the gates in such a way that you reduce the band gap a little bit. And typically that's what we do. And you can do like to reduce to about half a volt of the band gap. Then you just reduce the bias voltage that you need to apply to about half a volt, which is nicer. It suppress the tunneling if you don't apply that large A bias voltage. And yeah, you can play with, some of the engineering of the bands. So it's really like a material choice and then applying the gate voltage to bring to the point that you want. And it has sort of lots of experience in terms of picking what materials that you should choose to do it. Yeah.
So, let me ask a question. So can you speak more generally about comparing dichalcogenide, Moiré structures, and graphene?
Yeah.
Just, maybe at a very practical level, what are the advantages, disadvantages, and
I see.
because you presented a very nice picture where we can tune correlated physics, band physics, and so on, and interesting ground states. And graphene is the same with some flavors there.
Yeah, actually, yeah.
What do you see in the future?
Yeah, I can sort of, okay, it seems that there are two different questions. One is the future, one is the difference between the two. Actually, there are many technical differences between the two. For instance, graphene, you have only one choice. There's only one graphene, right? And for this TMDs, you have a bunch of them. So a bunch times a bunch, you have a lot of them combination. And that will really allow you to play with the band alignments to begin with, which you have no degree of freedom to play with that for the graphene. And the graphene, the flat band actually cannot be tuned by a vertical electric field. That's another main difference in terms of tunability. So graphene, you can stack more layer than you can tune. For instance, a 3-layer magic angle graphene you can tune, but bi-layer you cannot tune. And there are also additional difference in the degrees of freedom for the electrons. And there is also one big difference I want to point out for the graphene is that the graphene flat bands is caused by destructive interference of the tunneling of the electron. It's a competition between the interlayer tunneling and intralayer tunneling. So it's a destructive interference of the two processes that leads to this flat band. That's why you need them to tune just the magic angle in order to induce this flat band. Here, the bands are quite simple. You don't have a Dirac point to begin with for the parental material. You have a gap. Then it's really a zone folding picture to generate the flat bands. And so in many ways, the band structure, the underlying band structure is simpler in this system in the way that the Moiré bands are created. And graphene, of course, there are some practical advantages, especially you're doing transport measurement. You don't have much a problem of forming good contacts on this material. We struggle a lot with, playing with contacts in this material. So graphene is nice. You always can do, easily do electrical measurements on them. But on the other hand, you cannot really do optical measurement on the graphene. There's no feature and things like that. So it's really like they're totally different. And I think both are interesting that you have to, they just provide different paradigms for studying, correlation physics. Yeah.
Josh first.
Sorry, I just, a slightly more practical follow-up on John's previous question. So for graphene, using graphite gates was really important. And then I imagine with heteroconjugates this issue with air coder. But I wonder how important it is for TMD structures, first of all, to do it in a glove box versus air, just with these two materials. And second of all, it looks like using graphite gates, how important is that?
Yeah, so for these materials, we don't need the glove box. They are very stable. But if we are dealing with a molybdenite, of tellurium, that's you need a glove box to do that. And actually, that's the part I did not talk about, that we use the tellurium to generate these topological bands, because we need that to tune the band alignment, right? And so for that, you do need to do everything inside a glove box, which is a pain in the neck, yeah, but you have to do it in order to keep the material alive. And for graphite contacts, we typically use graphite contacts also.
Gates or
For the
contact?
gates, the contact, we use a bismuth for electron doping, for the platinum for hole doping. I'm not so sure how important that we, for instance, we replace the graphite gate with some other metal gate. We have done that. For instance, we changed the graphite gate to something like a layered metal gate, like the tantalum diselenide, which is a 2D layered metal. And it doesn't seem to change things dramatically.
What about just an evaporated gate? Like,
We have not really tried that actually extensively. So we cannot say about that. Yeah. The worry is that whether the evaporated gate is still as clean as this flash sheets of the metal gates, right? Maybe you worry that whether it's less clean, but I don't know how important that is.
So just a quick question, when you say graphite gate, does that mean you actually mount a piece of graphite on top?
It's a few layer graphene, so it's still very thin, but you just.
So it's the same process, but
It's the same.
graphene.
Yeah, it's the same process. Then you would pick up the graphene first, and you pick up the.
How many layers? 5 layers?
Yeah, typically a few layers on the order of 3 nanometer. No, 3 nanometers, 10 layer. I would say 2 nanometer ish.
Raj?
Yeah, I have a question related to the twist angle theta versus the lattice parameter of the Moore pattern.
Yeah.
There a continuous variation between the two, or you have some discrete values for which you get this lattice?
Yeah, so in the angle range that we study, it's in the very small angle range, it's continuous. Okay. So the Moore period, when you increase the theta, it will continuously decrease. Actually, I don't have a plot here.
So controlling the angle between the two layers precisely must be very challenging to the reproducible sample.
Yes, actually.
How do you control that?
Yeah, so that's why we are actually we are doing a lot of heterobilayers, because we just need to snap them at 0 degree, close to 0 degree. Then the Moore lattice structure is dominated by the lattice mismatch of the two material, not by the twist angle. So if you are doing twist angle, like the homobilayer, the 2 layers is exactly the same. And then the Moore period will actually change really, really fast.
Yeah.
At small angle. And that is interesting from a tuning point of view, but it's also annoying from a disorder point of view, that you always have some twist angle disorder in your material. And if the Moore period is so sensitively dependent on the angle, any variation in the angle will bring in disorder, will bring in just change in the Moore periodicity locally, then that's an issue for the homobilayer.
But when you are using 2 dissimilar materials like tungsten diselenide and
then that's not very important.
If the theta is not exactly 0 every time, you also have that twist angle problem.
Yes, but that's a lot less important, because I have to go back to the formula here. So this is in the 0 angle limit that you have a Moore period that's given by this guy here. Yeah, this guy here, only the theta, only the delta. But when you have a finite angle theta also, so you have delta and theta together, the denominator will change to square root of delta square plus theta square. So as theta, because they scales as theta squared, as long as theta is small compared to delta, it contributes a tiny amount to the variation to it. So if you have a larger lattice mismatch, that's very robust.
Okay.
Yeah.
Thank you. Nice talk. Question is, in one of your phase diagrams, so like electronic crystal.
Yeah.
You see density waves in these systems?
Yeah, I can. I think you can also call them density waves. to me, it seems that it's probably just my definition of whether we should call them an electron crystal or a density wave, is that if in a zero bandwidth limit, it's almost like it's only the classical electrons almost in that case. Then it's really like the Wigner limit, that is like a Wigner crystal. The electrons are like point charge particles, except the spin there. And they are well localized by the lattice. And then the Coulomb repulsion for them would just self-organize into periodic pattern. Then I would call it like an electron crystal. But if you go increase the bandwidth here, and the electrons, due to the quantum mechanical effect, will start to become more delocalized, then from side to side, the electronic charge density wouldn't be 100% modulation. For electron crystal, it should be 100% modulation. But for that, around here, right near the metal insulator transition, increase the bandwidth there, then the electrons start overlapping in the wave function. It's a charge density wave. In that case, I would call it a charge density wave. That the charge density has a modulation due to the Coulomb interaction, but it's not 100% from side to side. So maybe it's like 50% or even smaller. Then I call it a charge density wave. But I think they are pretty similar to each other. It's just how important the quantum mechanical effect.
It's always commensurate.
It's always commensurate. So these are happening only at the commensurate fractional fillings. Yeah.
My second part of the question is how do you experimentally detect that?
Detect these states. There are different ways. You can measure transport now. They are insulators because the charge are locked to the lattice, up into the lattice. And so in a small bias limit, they can upload current. And you can measure the compressibility of the system. And these states are incompressible. And when you dope a little bit away, they become compressible again. And there are different ways of measuring compressibility. You can measure capacitance, or you can just do yesterday what G said, that you can do optics to look at the dielectric response. So there are at this point, there are already many different ways that people already study this electron crystals, also including STM. They can directly image that as well. Yeah.
Any final question?
I'm trying to understand the picture in real space, how it's electron like distributed or binding of the function distributed in terms of the emergent magnetism. Talk about non-insulating physics picture. So okay, you have this upper and lower Hubble bands, and you only feel the lower Hubble bands. For those lower Hubble bands, what are the, let's say, in real space? Where are they located? Are they like AB side or AA side or?
Oh yeah, that whether it's AA or AB, that totally depends on the Moray materials of choice.
Right. In your specific case, for example.
Oh, in this case, I forgot whether it's AA or
But
or BA, yeah, AA side or AB side. I have to go back to look it up. Yeah.
Okay, so those mini bands are from the band bottom. So think about in the extended zone, they from the band bottom originally, right? Okay, so right after they open up the gap, so they still retain the original optical character. Right?
They retain. They will go to the Moray potential minimum.
Okay.
Whichever side, whether it's AA or AB, as long as it gives you the Moray potential minimum. I think it's the AB. Then the electrons are localized at that location.
And this spin is the real spin of the electrons.
Yeah, that's an interesting question. Whether it's a real spin or because of spin orbital interaction within each layer, it's a spin valley locked. So from a spin rotation point of view, it should be the pseudo spin. The valley, that is actually the spin of this Hubble model. But if you're talking about the outer plane magnetic field response, then the two are locked. Then the spin and the valley are the same in that situation. But the in-plane response is different. The in-plane magnetic field do not couple to the valley, unfortunately. So that you cannot really do a nice in-plane magnetic field study in this kind of system.
And this measurement was done by MCE?
Yes.
Okay, lots of great questions. So thank you. Okay, we have a coffee break. We're running a bit late, so we'll come back at 11:20.
You will have a prize if you come back on time.